Don't make the mistake I do and put it in the fragment shit. Welcome again. This time we create a material system. You ready? Put it in a put it in a fragment stage, man. God damn it. Oh, it works. It looks weird, but it works. Remember that you need to be on the branch 08 materials. We will be starting from this point. This time we start out in the game CPP file and we begin by typing in struct material. Our material system will hold color and the asset that it references, the texture. If you like what I do, consider tuning into my Twitch. I stream at 10 a.m. Central Eastern Time, which is 1 a.m. Pacific Daytime. You can also support me on Patreon. I've set up a new page. Supporting means getting access to the game code that I'm currently working on, which is Cake's Tower Defense. So we need the asset type ID, and something that is called material data. This material data will be sent to the GPU every frame. We will define this in a second. Let's first fix some includes. Include up here assets/assets.h. Then we should have the asset type ID. The next thing we need to do is we add a uint32t material count and materials array of max materials. And you guessed it, that is a const expression again. uint32t const expression max materials. Let's define this as 100 as well. Okay, the next thing that we need to define is the material data. And since we sent that to the GPU, we will define it in the shared render types. So go in here and create a new struct called material data. This material data will only hold color for now. So we define a color. I like to call it vec4 color. Since we don't have the vec4 yet, we need to define yet another struct. And this is going to be our first vector in a file called my_math.h. In this file, we pragma once, and then we define the struct vec4 to be a union, and I will explain what that is in a second. And then we do another struct for the color, actual color stuff, which would be a float r. Let's just yank this a couple of times. Whoops, not 5 times, but 4. G, B, and A. And the other structure that we define inside this union is an X, Y, Z, W. This R value will be the same as this X value. It is a union, meaning that the memory location of this float is the same as the memory location for this float. We could potentially interpret the memory location differently in here by not typing float, but uint32t. But yeah, just on a side note, if you don't know what a union is, because this is very powerful, as we can now access the individual parts as a vector or as a color. And so in the shared render types, we need to include, in the ifdef case, pragma once, include my_math.h, like so. And make sure that vec4 is properly spelled. Good so far. Go back into game CPP and check if material data is actually good. It's fine. Very nice. Next, I want to create a couple of functions below create entity. I want to create an internal uint32t create material function that returns a material index into the array that takes in the, we will take in the game state pointer, game state, like so, and an asset type ID, and a color or a vec4 for the color. And I like to initialize that to a default color, because I don't always want to supply it. 1.0f, if I can spell 1.0f, comma 1.0f, comma 1.0f, comma 1.0f. Default color of white. This create material function will first of all check, just like all the other functions with the descriptors, the render commands, we check against the maximum material count. So if game state material count is less than max materials, we can actually create one. Otherwise, we do a cakes assert here, 0 reached maximum amount of materials. And what I like to do on the top here is a uint32t material index. Define that as invalid_edx. If you don't remember what that is, we can inspect it. It's in defines.h. It's just the maximum value for uint32t. I like doing that because in the future we might error check if we could actually create a material or not. And then all we do is set the material index to game state material count. Then we also get what is called a material pointer m to the address of game state materials on game state material count ++. Increase the count that way. And we want to set the attributes of the material, the asset type ID and the m material data.color to the color. Below here we return the material index. That is the first function. It will help us create materials. But what if we want to get a material, right? We want to get a material for an asset that we already have. So I like to define another function, internal uint32t get underscore material. And it has the same parameters. So I guess I'll just yoink this real quick. Paste and then turn this into get material. It tries to get the material with these parameters. We'll do the same thing as above. The uint32t material index is invalid underscore index. So, and then we do a for loop uint32t i0 I is less than game state material count I++. And for every material that we find, game state materials on I, we check if m dot asset type ID is the same as the asset type ID and m material data dot color is the same as color. Then we set the material index to I and break. If we do not have a valid material index down here, so if material index is the same as invalid index, then we need to actually set the material index to create material based on the game state, the asset type ID, like so, and the color. And below we return the material index of this function. Now you notice we have a problem here. There is no operator defined. We need to define how to compare to vector force. We defined a new structure, but we don't know how to compare those two. So back in my math.h, we define what is called a bool operator. And then immediately after the operator keyword, we have to define the equal sign. Don't know why that is. I was expecting some sort of space between those when I first saw this, but yeah. Anyway, so it takes in a vector for other, and all we do is return if r is the same as other.r and g is the same as other.g and b is the same as other.b, like so, and a is the same as other.a. I'm using the RGB part here. You could also use X, Y, and Z and W. It doesn't make a difference. So we now have the operator and it should not complain anymore. It doesn't. And thankfully, it complains on another part. We don't use one equal sign, but two equal signs here on the asset type ID. Now we have a way to get a material index, but I also want to get a material by an index. So I can just get a pointer back and change the attributes of it. And I know this is a bit of boilerplate currently, but trust me, this will help you in the future. I'm doing this even though we don't need to right now. So I like to do another function here above init game, which is an internal material pointer get underscore material. That takes in a game state pointer, game state, and a uint32t material index. And all the function does is if check against the material index that it is less than max underscore materials. And if so, then we return the address of game state materials on material index. Otherwise, we return invalid edx. And I just noticed I don't like the return here. So define a material pointer up above m to 0. Return that below the if check, return m. And over here we set m to the address of this. That makes more sense to me. I just like doing it that way. Okay, now we have a way to get a material, create a material, and all of that stuff. So I would like to change the init game function quickly. Since we have a way to create materials now, we also need to connect it to the entity. And we could potentially just add it to the entity over here, to the structure. But I would like to add it to the transform in the shared render types. All I add here is an int material index. And the reason for that is that we can use it in the shader later on. It will make sense when we get there. So back in game, in the init game function, we create a material every time we create an entity, you know, just for fun, of the asset right cakes with a color of RGBA. And we set that material to e transform dot material index below. That should work. Okay. Now we just need to define R, G, B, and A. And I want to define them based on a counter. uint32t counter is 0. So basically I want to define a float R that is float counter divided by 100.0f. And that makes it so that once we reach 100 entities, our R value will be 1, meaning we have full red channel. And I would like to define a couple more floats here. The B channel to be 1.0f minus R. So basically they switch. And I don't know, the RGB A channel to be just like R over here. And notice that I put them out of order. Is supposed to be, I don't know, R as well. You can play around with these values. You know, just made them up real quickly. And then don't forget below here to counter plus plus, so that you actually change the values over time. All right, that should be it. Let's quickly check if the program runs like this. Build and run. We actually cannot compile a shader. Syntax error, unexpected identifier and shared render types 23. That makes sense because we define a vector 4 here in the shared render types, which is not known to GLSL land. In GLSL land, we do not use vector 4 like this, but we use that, a small vector 4. But then we can't compile our program. That is a problem. But the solution to this problem is very simple. In the if check for the cakesgen, we not only include the math.h, but we also define vec4 to be capital V ec4, like so. Now we should actually be able to compile down here. That works. And run if I didn't make any other mistakes. And the game still runs. Good. That was it for the game side. Now we actually need to change the renderer because we added materials and we need a buffer for those. So open VK renderer and go to the VK context and we add another buffer. Buffer, material, storage, buffer. And then we need to allocate it. For that, go down below into the VK init function where we create transform storage buffer and we create material storage buffer here in the local scope. We can yank everything from the storage buffer, most of it. We need a max materials count, which we have in the game. We need the size of material data. Don't take the materials here, but the material data. The buffer usage and the memory flags should be the same. Next, I want to change the entity loop in VK render because in the future, we will not be able to use this as easy. We cannot just copy over all the entities. So I want to add a for loop here for UN32T I0. Move that out of the way. I is less than game date, entity count, I++. And for every entity, E is the address of game state, entities on I. I want to get the material of it. Material pointer M is get underscore material. This is why we did the function game state and E transform.material index. We use that. And then we do the same thing from below here. We get the descriptor based on the asset of the material, M asset type ID. We check if we have one and we add a render command using that descriptor. Quickly delete this stuff down here. We have a bit more space. Now looking at this function, it won't make sense to set the transform index to 0 because now we actually have to create different instances of entities. So meaning different draw calls. And a different draw call means we have to index into the transform buffer at a different position. So the transform index 0 will be wrong here. And the instance count as well. Let's set the instance count to 1. And the transform index will be set by the add render command. How do we know how many transforms we have? Well, we need to keep track of them. And I like to do that in the VK context by adding another array, UN32T transform count and a transforms array of max underscore transforms. And you know it, we need to define this up here, UN32T const expression max underscore transforms. And I like to set this to max underscore entities. For now, going back to VK render down here, we can now inspect the VK add render command and set the RC push data dot transform index to VK context transform count. This will be the offset that we use. Going back to VK render down here, let's do another if check here. If we actually have a render command, we set the instance count to 1, meaning right now we will have 100 draw calls for the 100 entities. Of course, we will improve this later on, but it's not important right now. And down below, we need to copy the transforms to the buffer, but we also need to set the transform for every entity. So in the VK context, transforms on VK context transform count ++, we assign the E transform like so. And down below, we no longer use the entity count, but the VK context transform count, size of transform. And below here, we don't use the entities, but the address of VK context arrow transforms like this one. And one more thing, after we are done copying to the buffer, we do VK context transform count equals 0. Reset the transform count for the next frame. I'm not sure if that will work. I'm pretty sure I missed something. Quickly build and run. It says my buffer is too small. Interesting. 1600 by 200. Guys, don't copy paste, please. Don't ever copy paste. Don't be stupid. Okay, don't use this transform storage buffer but the material storage buffer here, please. Okay, then the program won't complain that your buffer is not big enough and you will cry like I do. Okay, build that shit. Look if that works. I didn't think it would work, but it does. Interesting. Okay, very nice. Very, very nice. We go back to VK render. Now we copy our transforms to the buffer. I suppose I want to do something else. Let me introduce another local scope here. Call this copy data to buffers. Boom. Put this in here. Yoink. In here like so, and I guess we put the local scope of copy transforms to the buffer here and say, well, entity rendering. Boom. Now we also want to copy vk underscore copy underscore to underscore buffer, vk context material storage buffer. Which type of data? Well, material data, and a count would be the size of material data times game state material count. And you notice that this is dependent on the game and not on the renderer. We don't care how many materials the renderer or something has. We look at the game. That's how many materials we have. This is how many we will copy. And so I tried out and I actually allocated material data array material data on the stack of max underscore materials. And that worked. That is 1600 bytes, I think. But we have to be careful not to stack overflow, meaning to exhaust our stack size. So I set the material data here, and I guess we need to do a for loop for uint 32t I is 0, I is less than game state, like so. A material count, I++. Boom, we do material data. I had material data. Material data on I is a game state materials on I dot material data. We assign the data and copy to the buffer. Let me center this a bit over here. Build this and check if that works. Still no error, which is good. But we are not using the material yet in the shader, so we need to open the shader.frag. We want to use the material in the fragment shader. In here, we need to create a new layout. Set equals 0 in the same set. Binding equals 3. A read only, because it's a storage buffer, buffer materials. And this just holds material data array, materials in small array. Like so. Don't forget the semicolon below here as well, just like with structures in C++. And also don't forget to include the shared render types. Don't forget that. We could try compiling right now, but we'll get errors because we have not defined the buffer in the descriptor set. We are not telling Vulkan that we are using a buffer here. So to save us some time, we need to define this. So go to vk init, where we create the descriptor set layouts over here. And we need to add another storage buffer below the combined image sampler for the index, and the last parameter is the index 3. That is the binding index, right? And then close the brace here and put a comma. That is the layout, but we also need to push this descriptor in the set, right? In the writes, where we write to the set. Basically, we need to set the pointer. We update the descriptor in our function vk create descriptor. If you remember from last time, over here, let me zoom up a bit. Over here, vk create descriptor, this function. Down here, we write to the set. We also supply the descriptor infos here. We need another one that matches a storage buffer like this, but we can't use the transform storage buffer. We need the material storage buffer. .buffer. And then down below here, we copy the write set function. Boom, 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 boom. Like so. And we take a storage buffer over here. We forgot to close the brace. The index over here is the second parameter below. That has to be 3. One more thing, we are not using the color yet. So in the shader.frag, we want to access these materials, but we don't know which index we have. We have the transforms in the vertex shader, but not in the fragment shader, right? The transforms carry over the material index. So in the shader.vert here, what we need to define is another out location. A layout location is 1 out, uint can also be int, doesn't matter, material index. This one, and then we just do material index is transform.material index. And in the fragment shader, we define another layout location is 1 in, and that has to be flat like this. That means whenever we supply something to the fragment shader, it will be interpolated. If we want to supply a flat value that is not interpolated between different vertices, we need to define it using the flat keyword. Oftentimes, this will also cause an error and it will tell you, please use flat here. That is the material index. Oh, I forgot the type here, which is uint. Like so. Don't forget that. And all we do is we multiply the color by the materials on material index dot color. And if I did everything right, probably not. Yep, didn't do everything right. What did I do wrong? Vertex shader 6. unexpected identifier, 6 down here. Oh yeah, I misspelled layout, which is very nice. Okay. VK shader stage fragment bit. I put the descriptor slot in the shader stage vertex bit, but not fragment bit, which is in the layout probably. Shader uses descriptor set. Put it in the VK shader stage fragment bit, not in the vertex bit. Don't make the mistake I do and put it in the fragment shit. Put it in the put it in the fragment stage, man. God damn it. Oh, it works. It looks weird, but it works. Almost. I wanted something else. I forgot to use the array index 3. We have been using this transform storage buffer. We need to put a 3 here. Very important. Then we build, and this is actually what I wanted to show you. Very nice. That's it. What I wanted to show you. If you want a challenge, I dare you, why don't you figure out how to batch these together? Let's say you create 3 different materials. You create a bunch of entities using these different materials, and you try to batch them together so that you have 3 draw calls at most. So down below here in this function, you don't add a render command for every single entity, but you try to make it so that you maximize the instance count. You have to do something to the entities to make sure that they are properly batched. I will be doing this maybe next time, maybe not, we'll see. But next time we will definitely create input. We need to input something. It's very boring if we only see stuff and we can never influence it. We want to move our stuff, right? Using buttons. So that's what we'll do next time. I will now do the Git stuff. So we git add dot. Everything we git commit -m. Edit a simple material system. Git checkout -b 09 input. Git push -u origin 09 _ input. And that's it. So yeah, thank you all for watching and see you next time.